Babies, welcome to our first video lesson here for physics. What we're going to focus on today is going to be on what's called one-dimensional motion and some of the basic variables of motion. So our goal is to focus on the idea of motion, and motion is simply, obviously, when things move. One-dimensional motion, however, refers to when things move simply in a straight line. So let's say, for example, that I have some little dude that's, let's say, going for a run. When I say one-dimensional motion, we can talk about this person running to the right or to the left. That would be a straight line. We could talk about that person going up or down. That would be in a straight line, like let's say he's jumping up or down. And the last one, which is a little tough, I can't really draw it on here, but let's say that he was going either out of the page or let's say into the page, okay? So one-dimensional motion refers to when anything is moving in a straight line. So we are not looking at, for example, if I were to take an object and throw it up into the air like that, where it would follow this sort of path, that is not one-dimensional motion because that object is moving both forward and up at the same time. That is what's called two-dimensional motion, and we're going to look at that later on in this year. So our goal for today is to focus on the basic variables of one-dimensional motion. Now, as we go through today, we are going to be looking at some things like distance, displacement, speed, and velocity. So you're going to hear all these new terms as we go throughout the year, and you learn some new concepts in physics. There are what are called scalar quantities versus vector quantities. And one of the fancy words you're going to hear throughout this school year is the idea of a vector, okay? So today we're also going to focus on the difference between scalars and vectors. So when we talk about scalars versus vectors, scalar quantities, a quantity is something that I can measure. A scalar quantity strictly refers to what's called magnitude. And think of magnitude as a fancy word, whoopsie daisies. Magnitude represents an amount. So an example of a scalar quantity would be something like money, would be something like time, because those can only have an amount. I have $100. That's an amount, okay? Whereas a vector quantity not only has magnitude, so we're still talking about an amount, but we are also going to attach to this direction. So for example, if I talk about this person that I had before that's going for a little run, that person can move. Let's say that he moves a distance of 5 meters. He can move 5 meters to the right. He can move 5 meters to the left. He could move 5 meters up. He could move 5 meters down. So because he's moving a distance of 5 meters, and we can also indicate the direction in which he moves, that would be considered a vector quantity. So there's some things that we are going to attach only the amount to, but there's other things that we'll throw on direction as well. So let's go through a quick example of identifying scalar versus vector. So as you go through this, think about, for scalar, just an amount. Vector has an amount and a direction. So in this first example, I have 5 meters. So 5 meters, notice that is just given to you as an amount. So 5 meters is technically a scalar quantity because the thing that's missing is direction. Next one, I have 30 meters per second east. East, I thought you meant west. Well, because we have a direction attached to that, that means this would be a vector quantity. Okay, next one, I have 5 miles north. Direction means vector. 20 degrees Celsius. Celsius, that's a temperature, that's an amount. That'd be scalar. 256 bytes, that's where you storage space in a computer. That would also be scalar. And then lastly, 4,000 calories, no direction in terms of calories, so that would also be scalar. So vector quantities are where we're going to see direction attached to those things. Notice here I have 5 miles north, 30 meters per second east. Both those have to deal with movement, but we indicate direction. So that brings up our first two variables of motion. So when we talk about when things move, movement means that you simply start at one position, and when you move to a new position, okay? So let's call this, for example, my initial and my final. So anytime I move, I'm going to move my position. So when we talk about the first two terms, distance, you guys probably know what this term means, but distance, think of it as like the length, is how far you move from your initial position to your final position. Okay? The key thing here with distance is distance we are looking at magnitude only. So we are looking at, in this case, what is the amount, the total length that you traveled from that initial spot to the final spot. Distance, we're going to measure in different units, but since we're going to deal with the metric system, we're going to measure this in meters. So that is going to be our base unit here for distance. So I can move, for example, 5 meters or 10 meters. Throw a prefix, maybe I'll move 10 kilometers. Now, we can also refer to something called displacement. Displacement is very similar to distance. The only difference is that we are going to indicate direction and pay attention to direction when we refer to displacement. So displacement you will see, for example, as 5 meters again, but instead of just 5 meters, you're going to have a direction attached to it. So 5 meters east. So here's a quick little example. Let's say that I have this motion. So let's say that whoever's moving here starts at this location in the top left corner. Okay? They move 4 meters to the right, 2 meters down, 4 left, 2 up. They move in a rectangle. So if I wanted to find the distance here, what I would do is just simply add up all those lengths together. So I would do 4 plus 2 plus 4 plus 2, and that would give me a total of 12 meters. But if I wanted to find displacement, which is slightly different, what I need to do is indicate the overall direction. So notice how I have 4 meters to the right to start. Okay? Now, what we're going to do is anytime I see something like right and left, up and down, I want you to think of a graph. Think of like the x and the y axis. When I move to the right on a graph, that's going towards the positive x. And when I move to the left, that's negative. When I go up, positive, down, negative. So what happens here with displacement is when I go 4 meters to the right, that's a positive 4. When I go 2 meters down, that's a negative 2. When I go 4 meters left, that's a negative 4. And when I go 2 meters up, that's a positive 2. So adding these up and paying attention to direction, I would have 4 plus negative 2 plus negative 4 plus 2. And if I add those things up, what I'm going to get is 0 meters. So in terms of displacement, here's what happens. I started here and I ended here. So technically, did I move? And in terms of displacement, because I started and ended at the same spot, I technically didn't move if I'm looking at direction. All right, so let's do a similar example without the diagram. So I have a dog that walks 12 meters to the east, 16 meters back to the west. I want to know what is the distance. I'll show this in red. And what's the displacement? I'll show this in green. So the distance, I'll just label D for distance. I'm just simply going to add those up. 16 plus 12, which gives me 28 total meters. So that would be my distance. If I look at displacement, I'm going to pay attention to direction. So notice it's 12 meters to the east, 16 meters to the west. If I think of, again, my little graph, north, south, east, west, east is technically going to be a positive direction, west is negative, north is positive, south is negative, just like I did before, thinking this as a graph. So when I go 12 meters to the east, technically that's a positive 12. But now when I go 16 meters to the west, I'm technically moving in a negative direction, so that's negative 16. So if I were to add 12 and negative 16 together, that's going to give me negative 4 meters. Okay? Now, negative 4 meters means this, and I'm going to draw this out for you guys. The dog starts here, walks 12 meters to the right or east. Then, in order to go west, has to turn around and go back this way and walk 16 meters to the west. So notice here, the gap or the difference between the two, he started here and ended over here, so that distance or displacement he traveled is technically -4. So that -4 really means 4 meters to the west. So if I ever get a negative displacement, that just means I'm moving overall in a negative direction. All right, next example, quarterback back pedals 2.1 meters north and then runs 7.4 meters south. I want to know again what's the distance and displacement. Again, I'll show this in red versus green. So distance I will do in red, displacement I will do in green. So distance, I'm just going to simply add the numbers together. So I'm going to look at the 2.1 meters, add to it the 7.4 meters. That's going to give me a total distance of 9.5 meters. Okay, just add them together. When I look at displacement, again, I'm going to pay attention to direction. So it is 2.1 meters north, 7.4 meters south. Okay, so north, think of that as positive, south as negative. So the displacement here would be 2.1, which would be positive, plus my southward motion of 7.4, which would be negative. And what I'm then going to do is add those things together, paying attention to the direction that they move, which will result in negative 5.3 meters, which means in terms of north and south, that the quarterback ended up 5.3 meters to the south. All right, next two examples I want you guys to try on your own. A little extra sass here. You're going to have a couple more values thrown into the mix, all right? So number C, you got the hockey puck, which is moving, and then number D, you got the football coach that's moving back and forth. So what would be the distance and displacement for each of those objects? Go ahead, pause the video, try these on your own. All right, so for the first one, you should get 42 meters. Just looking at the distances, all the values added up. And for displacement, should get 10 meters north, considering 16 is a southward motion, which would be negative. And overall, you get positive, so that's why it's north. For D, add them up, you get 56 meters. And for displacement, 12 and 22 are both westward motions, which are negative. The other two are eastward motions, which is positive, which would result in 12 meters to the west. All right, next part of motion. So again, motion relates to when I go from one spot to the next spot, my initial position to my final position. But obviously when you move, there is one little aspect, and that is time. It takes time for you to move from one spot to the next. And when you consider the time it takes for you to move, that is something called speed or velocity, okay? So speed just simply looks at the distance what you cover in a certain amount of time. So speed is going to be simply this. It is the distance traveled, but considers then the time it takes for you to travel that distance. So let's say that this distance up here is 5 meters again, and let's say it takes me 2 seconds to travel that distance. My speed would be 5 meters in 2 seconds, which would result in, I'll just write this as a decimal, 2.5 meters per second. So very quick in terms of units, how we describe speed, you're going to see meters per second. You might also be familiar with, you might be familiar with miles per hour. Okay, that's how we use it in the US system. But we're looking at how many meters you travel in a second. So that is speed. Now, we also refer to things in terms of speed as velocity. So velocity, the big difference between these two is velocity takes into account direction. So you'll see here in this definition, displacement, whereas speed takes into account distance. So velocity is simply going to be the displacement and a certain amount of time. Now, why this is different, and I'll draw it below, is if I were to travel, let's say, from that position and go 5 meters east, and then all of a sudden I change directions and go 10 meters west, notice how I'm changing direction here. So if I think of this in terms of what we just talked about, distance and displacement, my distance would be 15 meters, but my displacement, because that 10 is to the left, would be a negative 10. So the only difference you're going to see here in terms of what this looks like, let's say again, in terms of the time it takes, let's say it takes 2 seconds again. Here I'm going to get a displacement that is negative 10 meters and 5 meters, which is going to end up being 5 meters total. Sorry, negative 5 meters total. And the time of 2 seconds, the big difference here is that I'm going to get negative 2.5 meters per second. And that negative just simply tells me that my motion ends up being in the west or left direction. So speed and velocity are really the same thing. The big difference between the two is distance. Velocity is going to take into account the displacement you travel. I think I said distance. I meant to say direction is the big difference between the two. All right, so that when we talk about the average, okay, average speed and average velocity, keyword here, average. When we use the word average, the big difference here is that we're looking over a length of time, if that makes sense. So here it takes me a total time of 2 seconds to move. Down here it takes me a total time of 2 seconds to move. But sometimes I can refer to speed and velocity as an instantaneous. Key word within that is the word instant. Instantaneous speed or velocity would be your speed and velocity at a specific point in that time frame or in that length of time. So here's what this looks like. Take, for example, these two tables. I have my speed and position and time shown here. You'll notice that in this table, if we look at the position in meters, and I want to refer to speed, notice in this table that as the time values are going up by 1 every time, you'll see here that these values are going up by 6 every time, which means that this object is moving 6 meters every 1 second, which would be 6 meters per second. So the average speed here would be 6 meters per second. Now, where instantaneous speed or velocity comes into play is I want you to notice the second table. My time values are still going up 1 every time, so it's still per 1 second, but I want you to notice my values for distance or position. I go 1 meter, then 3 meters, then 5 meters, then 7 meters. So notice here how my distances are getting bigger. So this might be a time when I talk about instantaneous velocity or speed, because I might ask you guys, okay, how fast am I traveling at the 2-second mark? So at the 2-second mark, that is when I went 5 meters in 1 second. So I was going 5 meters per second. Okay, so my speed changes as I go through, and that is the difference of when I would use these two different terms, average speed versus instantaneous speed, or velocity if we're looking at direction. Okay. All right, 2 more examples here and we're done. So now we're going to look at actually calculating these average speeds. We're not going to look at instantaneous speed yet. We're just going to focus on the idea of speed and velocity. So let's say that I have our girl Lisa Carr. Get it? Lisa Carr. Heyo. It says she travels a total distance of 440 miles and her trip took 8 hours. What is her average speed? So notice here in this problem we have total distance. So when we refer to distance, our speed is going to equal our total distance divided by the time. So given the problem, the distance is 440 miles, and the time would be 8 hours. If I want to find the speed, all I'm going to do is take those two values, and I'm just going to divide them out. 440 divided by 8 would give me 55. Now, when I divide those out, it's technically 55 miles every 1 hour. It's like simplifying a fraction. The way we're going to write this is 55 miles per hour. Okay, and if it was meters and seconds, it'd be the same thing. We're thinking of meters per second or miles per hour. That would be the average speed. All right, now let's see if we can figure this out. So I'm going to give you guys some different things. I want you to match the speeds here in the following descriptions. So you have 6 descriptions here. I want to know which of these match up. So let's pause the video. What I want you to do is in each of those boxes, I want you to figure out the speed indicated by that, if you can, and figure out which ones match. All right, so the two that should match up would be in the top row would be that middle one, 16 meters in 2 seconds would simplify down to 8 meters per second. And then the first box on the second row would be averages a speed of 8 meters per second, literally telling you 8 meters per second. So those would match up. The first one, you just divide out, that would give you 4. In the third box, this one doesn't give you any sort of time, so I have no idea what speed is if I don't know what time is. So I need to know the time frame it takes to travel 4 meters. This one tells you the speed, a constant speed of 2 meters per second, but that doesn't match up. And then the last one, a little sassy here, it says it steadily speeds up from 4 meters per second in 2 seconds. Now, right away, that does not match what I had highlighted in yellow. However, you'll see that you are given the speed of 4 meters per second. So I wanted you guys to see this. Notice that this says that it's speeding up. And I want you to notice the first box also says starts at rest and travels 16 meters in 4 seconds. So if you start from rest, that means you're not moving, and you go to 4 meters per second, that also means you're speeding up. So the other two that match would be this one and this one. Those two would match because they both represent reaching that speed of 4 meters per second in a certain amount of time. Even though the times are different, we're reaching the same speed. So I got one matching pair. Now these are matching because they're moving at an average speed, and here you have two objects that are speeding up, reaching the same speed. Okay, so now recognize that there's a difference between moving at a consistent speed and moving at a changing speed. So if you guys got any questions, make sure you jot those down. A little bit of jargon. If you got any questions, shoot me an email or save them for in class, and we'll see you guys next time.